Last time we discussed about surface chemistry. Okay, surface chemistry, we discussed about physical and chemical adsorption. Then we discussed about Freundlich adsorption isotherm. This equation, adsorption isotherm. Okay, this equation is adsorption isotherm. Then we discuss about Langmuir adsorption isotherm. Okay, and this is the equation. Okay, so this is the equation, Langmuir adsorption isotherm. Okay, so we discussed about this. Now let us discuss about heterogeneous catalysis. Heterogeneous catalysis. Now, heterogeneous catalysis is basically adsorption. It is a surface phenomenon. Surface phenomenon. Let us consider reaction of gas. Reaction of gas on solid catalyst. Okay, solid catalyst. So we discussed about heterogeneous catalysis. Okay, suppose this is an example. This is an example of heterogeneous catalysis, where iron is the catalyst, this is solid, and we get ammonia. So here reactants are gases. Reactants are gases, nitrogen gas, hydrogen gas. Reactants are gases. And catalyst is the solid. So we will discuss heterogeneous catalysis in case of this type of reactions. Okay, reactants are gases and catalyst is the solid. Okay. Again, as we have already discussed, so this reaction, this catalytic reaction takes place on the solid surface. Okay, say as if this is the catalyst, as if this is iron. Okay, this is the catalyst, this is the iron, say catalyst. So here nitrogen is adsorbed. Nitrogen is adsorbed on the surface, hydrogen is adsorbed on the surface. Okay, then reaction between the two takes place. As a result, ammonia is produced. So this reaction between nitrogen and hydrogen takes place on the surface of the catalyst. So this is surface chemistry. So heterogeneous catalysis is basically surface chemistry because the reaction takes place on the surface of the catalyst. Okay. So Langmuir and Hinshelwood. Langmuir and Hinshelwood. Two scientists. Langmuir and Hinshelwood. Okay, two scientists. They proposed a mechanism. Of heterogeneous catalytic reactions. What is the mechanism proposed by Langmuir and Hinshelwood? Okay, let me write it like this: mechanism. Langmuir and Hinshelwood proposed a mechanism for heterogeneous catalytic reaction. So according to this mechanism, according to Langmuir-Hinshelwood mechanism, the heterogeneous catalytic reaction takes place in 5 steps. There are 5 steps. According to this mechanism, the heterogeneous catalytic reaction takes place in five steps. So, what is the first step? First step is the diffusion of reactants. Diffusion of reactants to the surface. Okay, that means this is the surface of the catalyst. So reactant molecules are coming. Okay, so initially reactant molecules were suppose here. Initially, say reactant molecules were suppose here. So here density of the reactant molecules is more. So they are diffusing. That means from higher concentration to lower concentration. Down movement of molecule, down concentration gradient. That is called diffusion. Okay, movement of molecules down concentration gradient. So what is concentration gradient? Suppose the molecules are moving along this direction, say x direction. Suppose the molecules are moving along x direction. So if there is concentration gradient, what is concentration gradient? That means dc dx is not 0. That means at each point, concentration is not the same. Okay, if at each point concentration is same, then dc by dx will be 0. But if at each point concentration is not the same, then dc by dx will not be 0. So we say that there exists concentration gradient. Okay, from higher concentration gradient to lower concentration gradient, the molecules move, and that is called diffusion. So molecules are coming from higher concentration to lower concentration. Diffusion of molecules to the surface of the catalyst. So this is the first step. Second step is the adsorption of reactant molecules. Adsorption of reactant molecules on the surface. Okay, adsorption. So molecules are coming, diffusion হৈ molecule surface লৈ আহিছে, তাৰপিছত কি হৈছে adsorption হৈছে. As a result of adsorption, energy is released. Okay, number 3, chemical reaction at the surface. Chemical reaction on the surface of the catalyst. On the surface of the catalyst. Okay, so say reactant molecules are coming to the surface, then adsorption. After adsorption, reaction takes place between the reactant molecules. Okay, so chemical reaction. This is the third step. Fourth step is the desorption of products. Desorption of products, product of molecules from the surface. from the surface. That means the product molecule, suppose this is the product molecule, this is the product molecule, suppose desorption means this bond, attractive force to the surface is broken. So what is desorption? That means the reactant molecules are bound to the surface. There is attraction between the surface and the reactant molecules. Okay. Now here what happens? This is the product molecule. The attractive force between the molecule and the surface is broken. That is called desorption of product molecules. Okay. Then fifth step is the diffusion of products from the surface. That means, so desorption হোৱা মানে কি এই attractive force to ছিঙি গৈছে, ছিঙি যোৱাৰ পিছত কি হ'ব? Now the product molecules move. There is higher concentration of product and there is lower concentration of product, so product molecules are moving. Diffusion of product molecules from the surface of the catalyst. Okay, so these are the 5 steps according to Langmuir-Hinshelwood mechanism. These are the 5 steps. Now here it is assumed that steps so this is the number 1 point. Reaction of gas on solid catalyst we consider, and this is Langmuir mechanism. And number 3 point is that steps 1 and 5 are usually very fast. So these 2 steps 1 and 5, these are generally very fast steps. They are coming and they are going. So these are very fast steps. Then steps 2 and 4 are also generally fast. Generally fast. Okay, so the third step is the step 3. Step 3 is generally the slowest steps. Slowest step generally. Okay, generally this is the slowest step. And step 3 means this is the chemical reaction. Okay, step 1, step 2, step 4, step 5, these are not chemical reactions. Okay, I repeat, step 1, step 2, step 4, step 5, these are not chemical reactions. So which is the chemical reaction? Step 3 is the chemical reaction, and generally this is the slowest step in the mechanism. And slowest step is called the hence it is the rate determining step. Let me call it RDS, rate determining step. Okay, obviously slowest step is the rate determining step. Okay, now Langmuir and Hinshelwood further consider that chemisorption chemisorption plays an important role in heterogeneous catalysis okay. That is why chemisorption takes place an important role, because because chemical bonds are are formed between adsorbate and adsorbent. Okay, so chemical bonds are formed between adsorbate and adsorbent. So chemical bonds are formed, that means more energy is released. Okay, enthalpy of adsorption is more in case of chemisorption. So more energy is released. So more energy is released. This will help in breaking the bonds between the reactant molecules. Okay, there is triple bond between the two nitrogen atoms. Okay, the energy released in chemisorption will help in breaking this bond, because this bond between the two atoms must be broken. Similarly, this bond between the two hydrogen atoms must also be broken, and new bonds between nitrogen and hydrogen will be formed. So in this reaction, what happens? This bond is broken, triple bond, this bond is broken, single bond, and new bonds are formed. New bonds are formed means energy is released. Bond is broken, that means energy is absorbed. Bond break হলে energy absorb হ'ব, আর bond form হলে energy release হ'ব. গতিকে adsorption হতে chemisorption হৈছে, so more energy is released. সেইখিনি energy কি কৰিব? এই bond বিলাক break কৰাত সহায় কৰিব. Okay? So chemisorption plays an important role. And chemisorption means here monolayer is formed. We have already seen in chemisorption monolayer is formed. That means one layer of molecules are absorbed. Okay, one layer, not this, not say one layer, two layer, three layer, not like that. Only one layer is formed, that is monolayer. Okay, next point Langmuir and Hinshelwood considered is that the rate of reaction okay, per unit surface area of the catalyst is proportional to the fraction of surface occupied by the reactant molecules. Okay, so we have already seen fraction of surface covered. Fraction of surface covered generally we represent as theta. Theta is the fraction of surface covered. Okay, what is fraction of surface covered? That means surface covered by the reactant molecules divided by total surface of the catalyst. Okay, surface covered by the reactant molecules divided by total surface of the catalyst. That is the fraction of surface occupied by the reactant molecules. So we discussed about this. And rate of reaction is proportional to fraction of surface covered. Okay, that means we can say that rate is equal to, say, k2 into theta, where k2 is the constant. Okay, so we'll talk about this. So we can write like this, or simply we can write, say, r is proportional to some constant k into theta. This is obviously because surface to surfaceৰ যিমানখিনি ঠাই ৰিয়েক্টেণ্ট মলিকিউলে অকুপাই কৰিব, তাৰমানে যিমানেই বেছি এডজৰ্পশ্যন হ'ব, বেছি সাৰফেসৰ বেছি ঠাই ৰিয়েক্টেণ্ট মলিকুলে অকুপাই কৰা মানে কি, কাৰণ এডজৰ্পশ্যন বেছি হৈছে। সো যিমানে এডজৰ্পশ্যন বেছি হ'ব সিমানে কি হ'ব, ৰিয়েকশ্যনৰ স্পীড বাঢ়িব অবভিয়াছলি, কাৰণ এডজৰ্পশ্যন হোৱাৰ পিছতহে ৰিয়েকশ্যনটো হ'ব। গতিকে মোৰ দি সাৰফেস ইজ কাভাৰ্ড, মোৰ উইল বি দি ৰেট অফ ৰিয়েকশ্যন। Okay, therefore r is proportional to theta, fraction of surface covered. Okay, so these are the different steps in the Langmuir-Hinshelwood mechanism of heterogeneous catalysis. These are the different steps in the Langmuir-Hinshelwood mechanism of heterogeneous catalysis. Now let us discuss about kinetics of unimolecular surface reaction. That means kinetics of heterogeneous catalysis. Surface reaction means heterogeneous catalysis. So kinetics of heterogeneous catalysis, and order of the reaction is 1. Unimolecular reaction means order of the reaction is 1. Now, what is the mechanism of the reaction? Mechanism of the reaction is like this. Suppose R is the reactant and it is gas. R is the reactant, it is gas, and S is the surface. Okay, S is the surface. Okay, then this will be adsorbed. Okay, this will be adsorbed. Suppose K1 rate constant, so we get RS. And backward process, that is desorption. This is adsorption. K1 is the rate constant of adsorption, and K minus 1 is the rate constant of desorption. So adsorption will take place, at the same time desorption will also take place. Okay, so this is the first step. In the mechanism. And what is the second step? Second step is the reaction. Okay, reaction. Rate constant is, say, K2 to form product. P is the product, and we get back the surface. Okay, So this is the chemical reaction, okay? And this is the chemical reaction, and here it is step 3, chemical reaction, okay? Here it is step 3 in the general mechanism, okay? Step 3 in the general mechanism, chemical reaction, okay? So these are the two steps in the unimolecular surface reaction. Step 1, adsorption, at the same time desorption, and step 2, chemical reaction. Okay? Now, according to Langmuir-Hinshelwood hypothesis, okay, according to Langmuir-Hinshelwood hypothesis or hypothesis, what he said, rate of reaction is proportional to fraction of surface covered. Rate of reaction is proportional to this. That is, R is equal to K2 into theta. This is the K2. This is the chemical reaction. This is the chemical reaction. Rate constant is K2. So rate of the reaction is proportional to this. Okay? And this is the slowest step. Okay? This is the slowest step. Slowest step. This is the slowest step. So rate of the reaction is this. Okay. So this is say equation number 1. This is equation number 1. Okay. Now, if we look at the mechanism of the reaction, that is this. So from this slowest step, what we get? From this slowest step, we get that R from this slowest step. Slowest step is the rate determining step. From this slowest step, we get that R is equal to, from this slowest step, we get that R is equal to K2 into concentration of Rs. We also get this because this is the rate determining step. So we get this. Okay. Now this is just like intermediate. This species is just like intermediate. Okay. This species is just like intermediate. So we can write rate of formation of intermediate from the mechanism. So what we get from the mechanism, due to this step, this is formed, so positive. Due to this step, concentration of Rs decreases, so minus. Again, concentration of Rs decreases, minus. Okay. So what will be this? This will be equal to K1 Rs, concentration of S, minus K minus 1 Rs minus K2 Rs. Okay. Now according to steady state approximation, dRs dt is 0. Okay. So what we get? So we get, say, K1 Rs. Okay. So this will be equal to 0. So let me write it like this. This is a 2. So from 2, what we get? We get this is equal to K minus 1 plus K2 concentration of Rs. So what is concentration of RS? Concentration of RS equal to K1 RS K minus 1 plus K2. Okay, so we are getting an expression. This is a 3, equation number 3. Okay, we are getting this. Now here in this reaction, when we write this, what we mean by this? That means this is the concentration of surface points. Okay, concentration of surface points, surface points for remaining means adsorption হৈছে, adsorption হোৱাৰ পিছত যিখিনি adsorption নোহোৱাকৈ আছে, ওকে, সাৰফেসৰ যিকেইটা পইণ্ট adsorption নোহোৱাকৈ আছে, ওকে, adsorption হোৱাৰ পিছত যিকেইটা বাকি আছে, that means adsorption নোহোৱাকৈ আছে, it means this. ওকে, কিন্তু এইটোতো আমি তেনেকে পাব নোৱাৰো একচুয়ালি, এইটো আমি তেনেকে পাব নোৱাৰো. ওকে, so what we do is that suppose let CS be the total concentration of the active sites on the surface. Okay, total concentration of the active sites. So this is the total concentration of the active sites. So what is the fraction of active sites covered? Fraction of active sites occupied is equal to theta. Fraction of active sites occupied, this is the fraction. Okay, this is the total total concentration of active sites. Out of this fraction is occupied by reactant molecules. That means what is the concentration of active sites occupied? Okay, that must be equal to CS into theta. Okay, so suppose you have say 100 rupees. Okay, say out of this, say 1/10 fraction has been taken by somebody. This is the total amount of rupees you have, and this is the fraction taken by some person. So what is the how much rupees have been taken by some other person? That is equal to 100 into this. That means 10. That means CS into this. তোমাৰ হাতত যেনিবা ইমান টকা আছিল, ইমান ফ্ৰেকশন কোনোবাই নিলে, তাৰমানে কিমানখিনি নিলে? this into this ইমানখিনি নিলে, তাৰমানে কিমান নিলে? 10 rupees নিলে. বা যদি তোমাক কয় যে 1/20 ফ্ৰেকশন নিলে, তোমাৰ হাতত 100 টকা আছিল, 1/20 ফ্ৰেকশন নিলে, তাৰমানে কিমান নিলে? 100 into 1/20, তাৰমানে 5 টকা নিলে, তাৰমানে CS into theta. So this is the fraction concentration of active sites occupied by reactant molecules. Okay, so what is the concentration of concentration of active sites unoccupied unoccupied. This is the total concentration, and this much occupied. This is the total concentration, this much occupied. So how much unoccupied? This minus this. Or we can write it like Cs 1 minus theta. Okay? That means that means that means concentration of S unoccupied, concentration of active sites unoccupied, that is equal to Cs into 1 minus theta. And concentration concentration of active sites occupied, that is equal to this, and that must be equal to concentration of this, because to occupy hoise mane ki iman thai occupy hoise mane ki himanta reactant surface complex form hoise, so this will be equal to this. Okay, so from 3 what we get, Cs into theta rs equal to Cs into theta K1 R into S equal to Cs into 1 minus theta divided by K minus 1 plus K2. So what we get? Cs cancel, Cs cancel. So what we get? Theta equal to K1 R 1 minus theta divided by K minus 1 plus K2, or theta 1 minus theta that is equal to K1 R K minus 1 plus K2. Hence 1 minus theta by theta, just reverse, that will be equal to K minus 1 plus K2 by K1 R. Okay, so I can write it like this. So what I can do is that I can do or 1 by theta minus 1 by theta minus 1, that is equal to K minus 1 plus K2 K1 R. So from this what I get? 1 by theta. So 1 this side. So what I get? K minus 1 plus K2 plus K1 R by K1 R. So I get this. Okay. Hence theta equal to K1 R divided by K1 minus 1 plus K2 plus K1 R. So we are getting one expression for theta. Okay, we are getting one expression for theta. So, and this is say equation number 4. And what is rate of reaction? So rate of reaction equal to K2 into theta. So this will be equal to K2 K1 R k minus 1 plus k2 plus k1r. Okay, so we are getting expression for the rate of the reaction. So we are getting an expression for the rate of the reaction. Okay. Now this equation I can write like this. Equation 5. So R equal to this. We can write 1 by R. If we write 1 by R, this will go up, this will come down. Okay. Let us do that. Hence, so from 5, what we get? 1 by R. 1 by R equal to k minus 1 plus k2 plus k1r, k2 k1r, k2 k1r. Okay, so this thing I can write it like this: k minus 1 plus k2 k1r, k2 k1r plus k1 this, so this will be 1 by k2, 1 by k2. Okay, 1 by k2. So we are getting one expression like this. Now why we are finding out this equation? Say this is equation number 6. Now using this equation we can draw graph. Using this equation we can draw graph between, say, 1 by r, 1 by r divided by 1 by r. We can draw graph. Okay, this side 1 by r, then 1 by r. We can draw this graph. Okay, so obviously what we get? We will get a straight line. We will get a straight line because this thing m equal to see, this is equal to m y equal to m 1 by r equal to x plus c. So we will get a straight line. So the graph will be like this. Graph will be like this. We are getting a straight line. And from this graph, we can find out the slope. We can find out the slope. We can find out the slope. This is a y, this is x. We can find out the slope. And slope equal to y by x, and this will be equal to k minus 1 plus k2 by k2 k1. Slope will be equal to this. Similarly, this is the intercept. This is the intercept. Okay, and this will be equal to c. That means 1 by k2. 1 by k2. Okay. Now, so this is the expression for the rate of the reaction. This is the expression for the rate of the reaction. Equation 5, this is the expression for the rate of the reaction. Now for gaseous reaction, because we are considering gaseous reaction, so for gaseous reaction, we can write pressure of the gas in place of concentration of reactant. For gaseous reaction, we can write pressure of the gas, pressure of R in place of concentration of R. We can write this. That's what we get. That's what we get for gaseous reaction. For gaseous reaction, R will be equal to K2 K1 pressure of R, pressure of R, pressure of R divided by K minus 1, K2 plus K1 and pressure of R, pressure of R. For gaseous reaction, we get this. So this is the equation 7. Okay. Again, we can write it like this. Again from 7, we can write it like this. Say 1 by R. 1 by R equal to say K1, K minus 1 plus K2, okay, by K2, K1 into 1 by PR plus uh, plus 1 by K2, 1 by K2. As before we have already done. As before, we can write it like this. So again, let us consider some cases. Say case 1. Case 1. Case 1, say rate of reaction. Rate of reaction. That is is very greater than absorption and desorption. Absorption means rate constant K1 and desorption means rate constant K minus 1, and rate of reaction, that means rate constant is K2. Okay, this is very greater than this. Okay, so what we can do? So K2 is very greater than let me see. So K2 is very greater than this. So what we can do? So we can write that K2 is very greater than K minus 1 and K1 R. Okay, we can write this. That so what we can do? So from 7, what we can do? R is approximately equal to K2 K1 PR divided by K2. So that is equal to K1 PR, or we can write in terms of concentration also. We can write K2 K1 concentration of R by K2, that is equal to K1 concentration of R. So we can write in terms of pressure, we can write in terms of concentration. So what we find? Say under this condition, what happens? Rate of reaction depends on one power of the reactant, one power of the concentration of reactant. That means the order of the reaction is 1. So this is first order reaction. So if the rate of reaction is very fast compared to rate of adsorption and desorption, if this is the case, then the rate of the reaction will be, the reaction will be first order reaction with respect to R, reactant. First order reaction with respect to R. Okay, so this is the condition. Next, so this is basically all about heterogeneous catalysis. Okay, I think this will be enough. You just follow this, and this will be enough, I think. Okay, say we can consider also, we can consider another case. Let me tell you another thing. Say, suppose another case, let us consider. Suppose K2, rate of reaction, is very very less than K minus 1 plus K1R. Okay, K1R. Reverse, just a reverse condition. If this is the case, then what we can write? We can write that from 3. We can write that not from 3. This is from 5. From 5, not from 3. From 5. From 5 we can write R equal to K2 K1 R. So we can, here we can neglect K2, okay, K minus 1. We can write like this. Now what we can do is that we can divide by K minus 1. We can divide by K minus 1. So K minus 1, that will be R plus, this is not this, this is plus K1 by K minus 1. This will be plus 1. This is plus 1, R, forward direction, absorption. So we get this. Now rate constant of forward direction by rate constant of backward direction, that is equal to equilibrium constant, K. Okay, and this we call absorption equilibrium constant. Absorption equilibrium constant. We call it absorption equilibrium constant. Okay, so I can write it. So R equal to K2 K R K R plus 1. So I can write it like this. Okay. Similarly, in terms of gaseous reaction, I can write it like this. R equal to K2 K pressure of R K pressure of R plus 1. So I can write it like this for gaseous reaction. This is the equation 8. This is equation 9. Okay, this is equation 9. Okay. Now here we can do one thing. So at very low pressure, okay, at very low pressure, what will happen? PR is less than 1. So in that case, from equation 9, what we can write? R is approximately equal to K2 K PR, and this is K PR, okay, K2 K PR less than 1. Oh, okay, no, this is 1, because this is less than 1, so we can write this is 1, so this will be equal to K2 K PR. Okay, or similarly Similarly, and, if we write in terms of concentration, this will be equal to K R. If we write concentration in place of pressure, it will be like this. That means the reaction is first order. This reaction is first order. Reaction is first order. That is, reaction is first order with respect to R. With respect to R. Reaction is first order with respect to R. Second condition, this is condition 1, this is condition 1. Second condition, at high pressure, at high pressure, then what we'll get, Kpr is very greater than 1. So in that case from 9, what we get, R is approximately equal to K2 Kpr, then Kpr, and this will be equal to cancels, so this will be equal to K2. This will be equal to K2. That means the reaction is zero order. Reaction is zero order with respect to R. So therefore, if we draw this graph, say R versus pressure of R. Okay, what will be the nature of graph? At low pressure, it will be first order. That means it will be like this. But at higher pressure, it will be parallel to this. At higher pressure, it will be parallel to this. Okay, and this is, you see, this is first order, order 1, and this is zero order. Okay, order 0. So this is all about heterogeneous catalysis. Okay, you just follow this. I think this will do. Okay, so I have completed 3 units of your syllabus, that is, and what are those? Number 1, chemical kinetics, and then catalysis, and then surface chemistry. I think you see this. If you have any difficulty, you just inform me. Okay, we will once again discuss in offline class. Okay, thank you.